Introduction to Hypergeometric Distribution. So I covered binomial distribution, I covered geometric distribution, and now I guess this is the third one. All of them are discrete with regards to these distributions, and they do share a little bit in common. Now, if you want to watch the binomial or the geometric distribution, you can go to the playlist from grade 12 on data management and probability, and you'll find them there. Now, if you've landed here and you want to watch the hypergeometric distribution, so that's the right place to be. And I will introduce this a little bit differently. I think that the hypergeometric distribution, if you look at it in particular, you take a look at the probabilities, the expected values, there's a ton of variables. So it's a little bit easier, I think, to start off with an example and then track back with regards to these distributions. Now, if you think back of what these probability distributions are all about, they basically take a certain number of trials. Geometric, for example, can take infinite. But within those trials, you want to see how the probability is distributed, okay, across all of those trials. And for all of these, you kind of have successes and failures that you talk about. And then between those successes and failures, you can figure out, okay, what is the probability? So what's the probability of having no success? What's the probability of having one success, two successes, and so on? So for this hypergeometric distribution, it's kind of the same. So I'm going to come back to all of this, okay? So where trials are dependent, success and failure, I think it's fine as long as you've kind of watched over binomial and the geometric distribution, so that won't cause you too much headaches. Now, the one key difference here is that the probability of success is not the same in each trial, okay? And then you'll see why. So let's kind of dive in, and then I'll come back and try to explain some of these terms to you, and then you can hopefully appreciate the random variable, okay, and then the probability distribution itself, okay, and then I'll use decimals to try to map it out for us as well to help us. All right, so let's imagine that, you know, we have this bucket, okay, or some kind of a box, and in this box, so we have, I guess, 10 different balls, okay, so we have green ones and then black ones, so 4 green ones and 6 black ones. All right, so now I'm going to kind of assume that picking, so I'll randomly pick a ball out of this box, and I'll assume that picking a green box would be success. All right, so I'm going to associate green, okay, with a successful pick. Okay, so that means that picking black would be unsuccessful. All right, so I have to be careful here so you don't think that's a 6. All right, so that's a G for green. All right, so now let's imagine, all right, that we're going to pick, and I'm just going to kind of pick this out of the blue. Let's imagine that we're going to pick 3 times out of this box, but we're not going to be replacing the balls. So if we don't replace the balls, okay, so if we don't put them back in, then the probability changes every time we would lift out a ball. So that shouldn't surprise us kind of from counting or learning about probabilities. So in that case, if we're going to pick 3 balls, let's imagine that I would say, what is the probability, okay, of picking 0 green balls? All right, so what's the probability of picking 0 green balls? Now you can say, oh, okay, so on the first try, what would have to happen is we would have to pick basically a black ball. Okay, so now picking a black ball on the first attempt, well, we have 6 out of the 10, so this would have been 6, okay, out of 10. Okay, so that's 6 out of the 10. That's the probability on the first one that we're picking a black one. Now, since we're saying that we're going to see no green ones, then on my second attempt, since I picked already 1 black one, So that leaves me 5, and then I have 9 balls remaining. So notice that the probability changes from one kind of trial to the next trial because we've already picked out a ball. So the trials are now dependent on each other, right? So they're dependent because it does depend on what you have picked out in the first trial. And then this would continue. So if I wanted to see another black ball on the third attempt, well, there would be only 4 black balls, okay, and 8 balls in total. So notice it went from 60% probability to basically 4 out of 8, which is 50% probability of picking a black ball. And that would have been, let me erase this, that would have been the probability, okay, of seeing no green balls. Now I can play the same game and then I can say, okay, what is the probability, okay, of hoping that within these 3, I would have picked one particular ball, okay, that would have been green. So I would have had 1 green ball, okay? And then I could say, okay, what's the probability that maybe out of the 3, 2 were green? Or maybe what's the probability that all 3 were green, right? So I can start playing this game and I can say, okay, well, so how many, okay, would I be able to have? And now, I went to 3, okay, so this was 3 because I said we had 3 trials in here, okay? So 1, 2, 3. It could have been 4 trials, right? It could have been 2 trials. If it would have been 5 trials, then we know that within 5 trials, let's say if you want it to be all green, that's impossible because we only have 4 green balls. But in any case, now instead of doing this for our probabilities, so sure, we can certainly find out what the probability like this is. But because we have done counting, it's actually a little bit simpler than this. We can just use combinations to be able to figure this out. So instead of doing all of this, right, where we're just going by probabilities, we know that, for instance, the probability, okay, of seeing no green balls, we would be dealing with something of this nature. Maybe I shouldn't have deleted that, but I guess I'll bring it back shortly, so I'll just show you that the probability is the same. So I could say, okay, well, what that really means is I have 4 balls that are green, but I'm going to choose none of them, right? Because I don't want to have any green balls. And then, okay, by the multiplicative kind of property, well, I would say I have 6, okay, black balls, or 10, which was in total, minus the 4 that are green. Okay, so I have 6, and I'm going to be choosing all 3 of them. Okay, so that is what I want to be able to have because I want to see 3 black balls and I want to see 0 green balls. Okay, and this would have been divided by, well, in total I have 10 balls and I'm going to choose 3 of them. So this is like saying, all right, well, what is the total number, okay, of possibilities that you can pick out, okay, these 3 black balls, divided by the total number of possibilities entirely. So this is something you have done, okay, if you have come across probability and come across counting and combinations. Now, if you would compute this entire thing, so, well, 4 choose 0 is just 1, and then we have 6 choose 3. So I guess, okay, so for 6 choose 3, and then 10 choose 3. So we can compute that. I'm going to do that just for this case. And then I'm going to compare it, okay, right here to what we originally started with, which was 6 over 10, 5 over 9, and then we had 4 over 8, okay, and it should be exactly the same. Well, 6 choose 3 is 6 factorial divided by, this would have been 3 factorial and 3 factorial, because 6 minus 3. All right, so this becomes now 6 times 5 times 4. That gets rid of one of these. And then divided by 3 times 2 times 1. The 1 is irrelevant, I guess. This is 2. And then 3 goes into this 2 times as well. So that is 2, 5. Okay, so 20. So that's what I would have had there on top. So that is 20. And then 10 choose 3. Okay, So for that, we have 10 factorial, okay, over 7 factorial, 3 factorial. I'll save us a little bit of time. All right, so popping out the calculator here so that we don't have to worry, okay, about this, divided by, so 7 factorial. All right, so that is equal to 720, and 720, sorry, divided by, this is 3 factorial, which is, I guess, 6. So we had 120. So this is 20, okay, over 120. So this is really just 1 over 6 for that. Now, if I started it off with doing, 6, so this would have been 6 over 10 multiplied by 5 over 9 multiplied by, okay, so 4 over 8. All right, and now let's bring it back in here. So it's 1 over 6. So that shouldn't surprise you. Now, so instead of doing this, I can actually find out with combinations exactly what the probability is. And now what we have is green is success, and then black, okay, was the unsuccess or just failure. Now, of course, I chose that arbitrarily. I could have swapped them. But the idea is that is in this hypergeometric, okay, distributions, we kind of are dealing with success and failures. And what we have is, so now you might probably start thinking that the random variable is going to be taking on, so this right here, is the number of successes that you have within the total number of trials or the experiments that you had. So you can have 0 successes, you can have 1 success, 2 success, or 3 success, okay? Or, I mean, it depends how many you want, right? So it is kind of identical to what we had in the previous distributions. And so for this, I can actually find out exactly what all of these probabilities are. Now, having probability of having 1 green, okay, isn't just so easily you would have to say, well, green can happen on the first trial, it can happen in the second trial, or it can happen in the third trial. And now you would have to figure out, okay, what is the total? Or you can just say, well, 4 choose 1, right? Doesn't matter where it happens. And then that leaves you 6 choose 2 of the black ones, divided by 10 choose 3. And you can do that, okay, for this, so now I'm kind of running out of space here. So I'll do, okay, a little bit of space like that. For having 2 green ones, well, I have 4 in total. I'm going to choose 2 of them. Okay, and then I'm going to have 6, and I'm going to only have 1 black ball. So that's the probability of that, 10 choose 3. And then for the last one, well, 4 choose 3, okay, and 6 choose 0. I don't have any black ones. And then 10 choose 3, which is the total number. So these are all the probabilities that we would have. And that's how we could order it. And now it doesn't have to, of course, be, balls that are green or black. It can be anything. You can be picking out anything you like. You can have males and females, and a certain number of males, certain number of females. And then you're interested in, okay, maybe success is, picking out a female, right? For your whatever it is. And then you can have a certain number of trials. So you will notice that this is actually a particular pattern that we have here. So we have the probability, so you're choosing. So you have, okay, you've labeled something as a success. So how many successes or how many, green balls did we have? We had 4, right? And then you're going to be choosing 0, 1, 2, and 3, right? Of those. And then you're going to be multiplying it by how many failures you had. Well, on the first one, if you have no successes, that means we had 3 failures. And we had 6 choose 3 out of those. And then you're always going to be dividing by the total number, okay, of possibilities, of combinations that we could have. So we had 10 balls. Choosing 3 of them, it would give us exactly, how many. So 120 in this case. So bringing all of this back to this distribution. So now you can hopefully appreciate that these indeed are dependent, right? The probability does change on each trial. So that's one thing. That is a little bit different than before. Okay, and now if I scroll back up here, so The trials are dependent. Now, we can pick how many we're going to have. And the total number of dependent trials, okay? So I have labeled it, but it doesn't have to be labeled this way. You know, I said R. R will represent the number of dependent trials. So in our example, R was equal to 3. So that's what I set. So for this one, you know, I said R, which is the number of trials, is going to be 3. Okay? Because we're going to be picking 3 balls without any replacements. Could have been 2, could have been 4. So now the other part is, okay, so as you go along here, you notice that we have 2 possibilities, the success and a failure. So that is, I have labeled green as success, okay, picking black would be failure, could be the opposite way around. Now the probability of success, notice, is not the same in each trial, okay? There are dependencies here. So that is important. So we don't have a P like we did in the binomial distribution or in the geometric distribution. Within here it changes. The random variable is the number of successful trials in the experiment that we had, right? So that is, you can appreciate that here is the successes was, all right, so how many green balls did you pick? 0, 1, 2, or 3 would have been maximum because we only have 3 trials to choose from, okay? So now next, the probability itself, right, is actually, so notice, I have labeled here M choose X, where X, okay, is the number of successes. So M on its own, as you see here, is the number of successful elements that you carry. For us, M was equal to 4. So for here, M was equal to 4 because we had 1, 2, 3, 4 green balls that I labeled them as success. So now you're going to be multiplying it by, so this right here, this is just simply, okay, n minus m, so n minus m right here is the number of unsuccessful elements that you have, where n just stands for the total number of elements to choose from. So for us, how many did we have in total? Well, n was equal to 10. We had 10 balls. 4 were green, 6 were black. So now n minus m, which for us is 10 minus 4, of course is going to be 6 because that's how many black balls we had, and we labeled that as a failure. So this example nicely illustrates all of these, and this is for all hypergeometric distributions. If they fall into this pattern, then it's called a hypergeometric, okay? And then the distribution just simply means how the probability is distributed across. Now, what is also interesting is that once you have these, you can find the expected value, okay, which is equal to R, which is the number of dependent trials, multiplied by M, which is the number of successes, divided by N, which is the total number of elements that you have. And I did a proof of actually this, you know, how does the expected value equal that? If you're interested in those proofs, I'll put up a link up above there for you. Okay, now how would we graph this distribution? So for all of these, of course, you know, if I have all of this, I can certainly calculate what the probabilities are for all of these. That's not a problem. But as you know, I really enjoy, okay, labeling and putting these into kind of decimals. So I, you know, set this in decimals. So notice that within here, okay, so what I have, and maybe I should, you know, bring this back on top there. So I've said I is equal to, so that's the total number of elements, where R, okay, is number of trials, as I said. Well, our number of trials is 4 because, sorry, number of trials is 3. We're picking 3 balls randomly out. M is the number of successes. For us, the success was the green ball, so I put it as 4. And then, okay, within here, you know, you can actually choose out of the functions. You'll find it within the functions button. So within here, for me, it's all the way actually at the bottom, and it's under number theory. So n choose R. So I have inputted this, Okay, and that is this formula that I have within here. That's the probability for each, where I have set m choose x multiplied by n minus m choose r minus x, and then at the denominator n choose r. All right, so that is my probability for each. N is just simply the number that I have. So in our case, so n, okay, was equal to the number of elements in total. And then I can plot them in, and here's my probability. So here, notice 1 over 6 is indeed 0.1666666, etc. So it mapped those out for 0, 1, 2, and 3. Now, the interesting part is, okay, and this is what you should notice, okay, I didn't really point this out in here, but if I go back, okay, so let me zoom out in here. So what you have hopefully noticed, or maybe you haven't, because I didn't point that out, I said, just be careful here, okay, with this. I said m is greater or equal to r. Well, m is the number of successes, okay? Now, if you make r, I mean, r can certainly be bigger than m. The only problem is if you're going to be choosing, let's say, 5 balls or 6 balls, well, it's impossible to get 5 green balls, right? So those probabilities are going to just be 0. And you would see that, okay, within here. Let me go back into decimals. All right, so here coming back to decimals, so notice if I make r actually bigger, let's say if I make it 5, you will notice that 5, the probability is 0. And that should make sense to you because you can no longer have that many green balls, right? So if this was, 7, okay, and so on, you're going to run into problems within here. So that's what we would have in there. Okay, so that's the hypergeometric distribution, and you can graph it. You can take on numerous examples, and I hope that you found this semi-useful in terms of an introduction. So that is it for this video, and hopefully we'll see you in a future one. Okay, bye everybody.